Okay, so let us start. So today we are going to discuss curve tracing. So as the name suggests, given a function, to draw the curve is nothing but the curve tracing, right? So suppose if it is a simple equation like y is equal to mx plus c or y is equal to 2x plus 3, then you can straight away say that this is having a slope of 2 and a y-intercept of 3. So this is a positive slope and this is how the curve is going to be. This is a simple curve. But actually, suppose if it is a complex curve, so if I give that, so x square into y square is equal to 3x or 3x plus 2. So if this is the curve, then how you are going to trace it? So these are the kind of questions that we should be answering it in today's class, right? So for this kind of cases, what we are going to do is, so we have to identify some important aspects of the curve, and those important aspects you have to identify it, and then at a glance you should be able to identify the shape of the curve. So that is the whole intention of this particular topic, right? So when you are identifying the shape of the curve, so one is you are identifying one shape, along with that the important points that are associated with the curve also has to be identified. Then you can completely describe that particular curve. Got it? So this is what is nothing but the curve tracing. Now let us see what are the important points that are there in case of curve tracing. So you can imagine simply the first and foremost is the axial intercept. So axial intercepts, we mean, suppose given a random curve, let us say there is a curve like this. Now this curve, it is intercepting at this particular point, at this point, and at this point. So these are intersections with respect to the standard x-axis and y-axis, and these are called as the axial intercepts. So this point, and this point are nothing but axial intercepts. So the intersection points of the curve with the x and y axis are called axial intercepts. So this is one of the important feature of any random curve taken, right? So, and along with that, the other thing is the domain of the curve. So domain of the curve, we mean, suppose if I give the equation y is equal to root x. Now for this curve, if I notice, so for negative values of x, the curve is imaginary. So what is your question? What about the other 2 points on the negative x and y axis? See this. So these points also, I missed it. These points also, all the points wherever it intersects, all those points actually needs to be considered. That's what we call as the axial intercept, right? Yeah. Here, so the domain of the curve in this equation, y is equal to root x. Y is equal to root x, we mean only positive values of x only satisfied, right? So if x is greater than or equal to 0, then only y is defined with a real value. But if x less than 0, then y is imaginary. So if y is imaginary, then we cannot trace a function, right? So then the curve is nothing but y square is equal to x. So y square is equal to x is fine, but y is equal to root x is not okay on the negative side of x. Got it or not? So here y is equal to root x. So this equation is nothing but, so this is the curve. Got it? Now here, if you notice, there are no values on the negative side of y. Got it? Negative side of y, actually you cannot find it, or you cannot find the values on the negative side of y, x also, right? So this part is called from 0 to infinite is the domain of the curve. So wherever the function gives only the positive values or non-imaginary roots, right? Non-imaginary values. Those are the values where the function is defined. So we have to identify the domain of the function is 0 to infinite. Got it? So these are the important points. So for a random curve, you may consider all the aspects, or you may be considering depending upon the case by case whether it is applicable or not. Got it? For some cases, this may be applicable. For some cases, it may be applicable. Some cases, the curve may not intersect the axial. So such kind of cases also can be there, right? Suppose if the curve is, let us say, if this is the curve, then there is no point in tracing for the axial intercepts because it is not intersecting. Got it or not? Suppose if it is simply U kind of shape, not a parabola, then it is not intersecting with any of the coordinate axes there. Got it? See this. What I am saying is, the points whatever we are discussing, one is the axial intercepts, another is the domain of the function, and whatever the other points also which we are going to find it out, right? All those points, don't try to think that for a given function, all the aspects are relevant. For some functions, it may be relevant. For some functions, it may not be relevant. So you have to consider on case by case aspect. Got it? In some cases, only axial intercepts are required. In some cases, axial intercepts may not be required. Because if I take a curve like this, completely U-shaped, where if it is not intersecting the x-axis and y-axis, suppose if it is bounded with the asymptotes like this, then there is no point in tracing for the axial intercepts for this particular curve. Got it or not? Understood, Vishal? So that's why, as I am discussing all the aspects of the curve, so some aspects may be relevant to some curves. All the aspects may not be relevant to all the curves. Got it? So this is the domain of the curve. And the next one is stationary points. So stationary points, we mean the derivative of the function is equal to 0. So this is nothing but the points where the tangents are parallel to the x-axis. Where the tangent to the curve is parallel to the x-axis. Is parallel to the x-axis. So you just actually go through the video. I just started curve tracing. So for curve tracing, we mean, so the definition of curve tracing is identifying the important aspects of the curve. So the important aspect of the curves are, so one is the axial intercept, another is the domain of the curve, another is the stationary points, and so these are the 3 points actually we just discussed it. Got it? Yeah. So this is the stationary point where the tangent to the curve is parallel to the x-axis, which means maximum and minimum points actually we calculated these stationary points. Suppose if the curve is taking turn there, then the slope there is coming out to be 0. Then you can identify that as one of the stationary points. So this is as if like the maximum or minimum. Got it? And then axial intercept are nothing but the points where it intersects with the standard xy coordinates. And the domain of the function is where the function value is defined. Suppose if you take y is equal to root x, in this only the positive values of x is only applicable. That means you will not find the curve on the negative side. Got it? So this curve it's not on the left side. Got it? Okay. So these are the important aspects. You just note down this. And one more important aspect is asymptote. Asymptote. So asymptote we mean, so here asymptote is nothing but, let us say, suppose if I take the curve y is equal to 1 by x. So I take y is equal to 1 by x. Then this is nothing but xy is equal to constant, xy is equal to 1. And this curve, if you notice, this is a rectangular hyperbola like this. So this is a rectangular hyperbola. For this particular shape, what is happening is this line, the horizontal x-axis, and this line, the vertical y-axis. So if you notice, these lines are bounding this curve. And then if you keep on draw this particular curve at infinite or at minus infinite value of y, so these two are going to join together. Here also at plus infinite, these two are going to join together. And here also at plus infinite of x value, curve will join together. Here also at minus infinite, these two are joining together. That means this curve will never touch or will never cross this line. And this line for this curve we call as the asymptote. So these two are nothing but the asymptotes. So asymptotes are nothing but the straight lines which binds the curve to a boundary and meets the curve only at infinite is called as an asymptote. So it is called as an asymptote. Now here in this case, in case of y is equal to 1 by x equal to 0 and y equal to 0 are the asymptotes. Got it? Crossing a particular axis. Here the definition of the asymptote is with respect to the curve, not with respect to the axis. Suppose if I take one more like this, suppose if I take the curve y is equal to 1 by x minus 1. So if you try to draw the graph of this, this will be y into x minus 1 equal to constant. The same curve is shifted to x is equal to 1. Now if I draw the curve like this, so this is x equal to 1 straight line, and this curve is like this, and then this curve is like this. If you notice, x equal to 1 line is binding now. It is crossing the y-axis. Got it, Ras? So this is the y-axis. This is y-axis, and this is x-axis, and this is x equal to 1 line. Now here, this is crossing the y-axis, but it is not crossing x is equal to 1 line. So x is equal to 0 line it is crossing. And this line is called as an asymptote. So for this particular curve, the asymptotes are, one is y is equal to 0 and x is equal to 1. These two are the asymptotes. Got it? You can note down this. So there are three different kinds of asymptotes. One is asymptotes parallel to x-axis or horizontal asymptotes. The second one is vertical asymptote. And the third one is oblique asymptote. So these two are by meaning actually So this is the horizontal asymptote and this is the vertical asymptote. Suppose if a curve is bounding with a straight line with some angle, then that's what we call as the oblique asymptote. Now actually I'm going to discuss one by one. So this is containing both vertical asymptote and the horizontal asymptote. So x is equal to 1 is the asymptote here and y is equal to 0 is the asymptote here, right? Horizontal asymptote is y equal to and vertical asymptote is always x equal to. So that is the kind of asymptotes you can get it in a random curve. Got it? Note down. So first case is horizontal asymptote. So horizontal asymptote we mean as y tends to infinite, as x tends to infinite, y tends to k, then the asymptote is called as a horizontal asymptote. And the vertical asymptote and this principle actually we will be using to find out the asymptote for most of the curves. And the vertical asymptote we mean here as y tends to infinite, x tends to some constant k, then the asymptote is a vertical asymptote. Oblique asymptote. Finding out the critical points, right? So it is good to find. So most of the times actually it exists, right? So finding out the stationary points or the critical points, take the derivative and equate to 0 and try to solve the points. And those points, if you notice it, that will be useful. Or actually it is advantageous to give more score. Got it, Raj? Oblique asymptote. As x tends to infinite, y tends to or y equal to mx plus c, then this is called oblique asymptote. Got it? So these are the different kinds of asymptotes that we will be thinking of, because while tracing the curve, these are all one of the important points. Got it? I'll give one problem. Y is equal to x minus 1 by 2x minus 3. Y is equal to x minus 1 by 2x minus 3. Find the asymptote equation. What is the equation of the asymptote for this? No. So we don't write usually y tends to infinite, x is equal to my, something like that. Why? Because see this, oblique is having some angle. So that's angle we always treat with respect to the x-axis, and then that will always be a straight line. A straight line is usually expressed as y is equal to mx plus c. So that is the standard convention. But it's not a rule that you should not be writing as y tends to infinite, x is equal to. Even though if you write that way, you are going to get the equation. But the standard convention is y is equal to mx plus c. Got it, Ross? Yeah, but so what is the equation of asymptote? So y is equal to 3 by 2. I think it's not correct. No, x equal to 3 by 2 is also not correct. Why 3 by 2? Anybody else? See this. So by definition, as x tends to infinite, y should approach a constant value k, and this is nothing but the equation of the straight line, or this is nothing but the equation of the asymptote. Now in this case, if you want to take x tends to infinite, y can be written as 1 minus 1 by x divided by 2 minus 3 by x. So limit x tends to infinite, then this is going to be 1 by 2. So y is equal to 1 by 2 is the equation of the asymptote. Got it? Note down one more. Y is equal to x square by x square plus 5. What is the equation of the asymptote for this? What is the equation of the asymptote? Yeah. So Raj gave correct answer. Yeah, that's correct. Y is equal to 1. So here plus 5 and minus 5. This leads to 1 minus 5 by x square plus 5. Now here, as x tends to infinite, this part will become 0, and y is equal to 1 is the equation of the asymptote. Got it? Y is equal to x plus 10 by y is equal to x by x plus 10 by 10x square plus 1. What is the equation of the asymptote? Y equal to infinite cannot be an asymptote at all. So this is one case of oblique asymptote. And the equation of the asymptote is y is equal to x. Why? Because as x tends to infinite, this part will become 0 and the curve is bounded between y is equal to x. Got it or not? Yeah, exactly. Y is equal to x will be the asymptote. If you trace this curve, this is as if like, so this is y is equal to x line, and then this curve you are going to get it as like this, and this point is at y is equal to 10. That is when x is equal to 0, this part will be 10, and this is the line y is equal to x which will bind this curve. It will not cross this asymptote at all. And this is the line which is called as the oblique asymptote for us. Exactly, right? As x tends to infinite, y will become x. So these two will meet at infinite. So as x keeps on increases to infinite, correspondingly these two are going to join together at infinite. So that's why this is nothing but the equation of the asymptote. Got it? Yeah. Any questions on this? I'll give you one more equation. Y is equal to x square by x minus 1. Y is equal to x square by x minus 1. What is the equation of the asymptote for this? Yeah, that's correct, Abhinit. Got it? Here, y is equal to x square by x minus 1 can be written as minus 1 plus 1, and this is x square minus 1 by x minus 1 plus 1 by x minus 1. So this can be written as x plus 1 into x minus 1 divided by x minus 1 plus 1 by x minus 1. So this is, these two will cancel, x plus 1 plus 1 by x minus 1. So this is the y, and this is the actual curve in a simpler format. So as x tends to infinite, this part will become 0 and y will become x plus 1. So this is the binding curve. Got it? So this is how you will be identifying the asymptotes of the equation. Got it? Based on this understanding, note down on problem. Trace the curve y into x square minus 1 is equal to x square plus 1. So first you need to identify this curve. Try to trace on your own first. So downward parabola between minus 1 and plus 1 is correct. Other than that, what are the equation of the asymptotes for this? Y equal to 1, that is one asymptote, and x equal to plus or minus 1, that is another asymptote. Now here, this curve y is equal to x square minus 1, x square plus 1 divided by x square minus 1. Now, as x tends to infinite, y will become 1, because this is 1 plus 1 by x square divided by 1 minus 1 by x square. Limit x tends to infinite, so this will be 1. So y is equal to 1 is one asymptote. And then if there are any vertical asymptotes, we will check that. So for vertical asymptotes, so this is x square minus 1 is equal to x square plus 1 divided by y. As y tends to infinite, right? As y tends to infinite, then this will become 0, right? So if this becomes 0, x square minus 1 equal to 0, or x square is equal to 1, or x is equal to plus or minus 1. So total there are 3 asymptotes are there. All these 3 asymptotes are, one is, so this is the coordinate axis, this is the x axis, and this is the y axis, and then so x is equal to plus or minus 1. So this is 1. Let us say this is one asymptote, this is another asymptote, and then y is equal to 1 is this asymptote. So this is one asymptote, this is one asymptote, and this is one asymptote. Now this is the x axis for us, and this is the y axis for us. Okay, fine. Now here the curve, actually if you try to trace it, y into x square minus 1 is equal to x square plus 1. Now at y is equal to 0, so what is the value of x? So if y is equal to 0, then x square plus 1 is equal to 0, which essentially means that there are no real roots. That means it will not pass through origin, right? So at y is equal to 0, so it is not passing through the x axis. So it is not touching the x axis. Obviously it won't pass through the origin. And then I'll take the other way. Suppose if x is equal to 0, then this will be minus y is equal to 1. So y is equal to minus 1. Y is equal to minus 1 at x is equal to 0. So y is equal to minus 1 is this point, and at x is equal to 0. So 0 comma minus 1 is this point. Then the curve is bounded between these two lines and these two lines and these two lines. So that means it will be like this. Like this. Got it? So this point is 0 comma minus 1, and this line is x is equal to plus 1, this is x is equal to minus 1, this is y is equal to 1. Now if you want to identify whether it is taking turn exactly at this particular point, you have to take the derivative of this particular function and equate to 0, so that you can find out the critical point or the stationary point. Now let us do that. What is the derivative of this function? So dy by dx. Can you tell me? So note down this. I am going to erase it and do the derivative. So the derivative of the function, so y dash is equal to minus 4x by x square minus 1 whole square, I think, right? Yeah, minus 4x by x square minus 1 whole square. And then if this is equal to 0, then x equal to 0. Got it? So x is equal to 0 is the point where the y dash value, right? So this is coming out to be 0. That means at x is equal to 0, there is a tangent which you can draw parallel to the x axis, because the derivative is 0. That means there is a tangent that exists at this particular point. Got it? So here that means the curve has to take turn at x is equal to 0. So that's why this curve is drawn this way. So these are the important points that you have to identify as part of this. Got it? Yeah. Any questions on this? So this is nothing but finally what we have done here is, so whatever is relevant points that are applicable, like finding out the asymptotes and identifying the critical points, and then if there are any intersection points with any of the coordinate axis, that we have to be identifying it. Now in this particular case, none of the places actually it is intersecting with the coordinate axis. That's why we didn't even ask us to find out the intersection points. What is your question? Slope is equal to 0 at x is equal to 0 because y dash value. So we tried equating to 0 and the corresponding x value is coming out to be 0. Now x is equal to 0 is the location where y dash equal to 0. Because we are intended to find out y dash is equal to 0 where there is a possibility of maximum or minimum occurs at that particular point. So which means there is a tangent that occurs at that particular point. So this is one place that is happening. This is the only place that is happening. Got it? Yeah, slope at x is equal to 0 is 0. Exactly. Clear? So this is how you will be tracing the curve. So in case of polar coordinates, right, what happens is, so polar means, so there will be a pole and there will be a r. So together will form the polar. That means, suppose if I take the curve, r is equal to a into 1 minus cos theta. Now here, this is a polar coordinate system. So there are no x, y's are involved in this, right? So there is a relation between the Cartesian coordinates and the polar coordinates. So if this is x-axis and this is y-axis, and then if you wanted to identify the location at one point, this point coordinates are x comma y, and then the same point you can identify in polar form, that is with a radius of r and making an angle with the theta, with the x-axis. So this angle theta, r comma theta, is the location of this particular point, which is represented by x comma y in case of Cartesian coordinates. And the corresponding relation between these two is x square plus y square is equal to r square, and tan inverse of y by x is equal to theta. So this is the relation between these two. And if you want to convert the other way, x equal to r cos theta, and then y is equal to r sin theta. So this is the brief about the polar coordinate system. So in this coordinate system, if you overlap both Cartesian and polar coordinate system, you will be finding out x, y, r, theta like this. But if it is purely polar coordinate system, then only r and theta will be there. Now in that, two important aspects you have to be aware. One is the pole, and the second one is initial line. So this is the convention. So here, if you draw a line like this, a horizontal line, we call as the initial line. And then from where you started counting the radius, that point we call as the pole. So this point is pole. Now for this particular polar coordinate system, r is equal to a into 1 minus cos theta. If you draw a perpendicular line at the point like this, then at theta is equal to 0, that you have to count it from the initial line towards the right. That means the angle should be changing from anti-clockwise direction like this from the initial line. So if you are keep on increasing the theta that started with 0 with respect to the initial line, you have to increase the value of theta and find out the corresponding value of r and identify the location as a radius, and then try to trace all such kind of radius so that you will arrive at the curve like this. Got it? Now here at theta is equal to 0, I have got the value a into 1 minus of 1, which is equal to 0. That means the radius value is 0 at theta is equal to 0. I'll just draw the line here. So this point is 1 radius. Now I calculate at theta is equal to pi by 6, that is at 30 degrees. So cos pi by 6 will be root 3 by 2, 1 minus root 3 by 2 into a, right? Yeah, so 1 minus root 3 by 2 into a. So this will be somewhere around some value, you are going to get it like this at 30 degrees. Now at 45 degrees, 1 minus 1 by root 2 times of a. So that will be somewhere here like this. And then this is the radius at 30 degrees. This is the radius at 45 degrees. And then at theta is equal to 60 degrees, I am going to get 1 minus 1 by 2. That will be somewhere around a by 2 like this. Now all such kind of points, actually if I try to trace it, now this will be starting like this and then going like this. So exactly at theta is equal to pi by 2, this value is coming out to be exactly a. That means this height, whatever we are going to put it here, this value is a. Got it? This value is a. Now, if you keep on increase the value more than the 90 degrees, let us say 120 degrees, that is 2 pi by 3. So 2 pi by 3 is nothing but the negative value of cos, that is cos 90 plus theta, right? So this will be, so it will 1 plus something. That means a positive value which is more than this. That means you are going to get a better value like this. So that is at 120 degrees. Now, this is how you are going to get it. So the same thing will be continued like this, and then you are going to arrive at one particular point like this. Now exactly at 180 degrees what is happening is cos theta is minus 1, minus of minus is plus, so 2 times of a. So this length is nothing but 2 times of a. 2 times of a. Now if you again keep on increase the value, this will be symmetric about the initial line. So this is the kind of shape what you are going to get it. Got it or not? Yeah. Got it? So symmetric about the initial line. And if you draw a tangent at this particular point, that will be perpendicular to the radius line. So this is radius line. This is exactly at 90 degrees. So this point, so tangent is perpendicular. Perpendicular to the radius at theta equal to pi. Got it? And theta is equal to, theta is, so at this particular point if you draw the tangent, this will be exactly, it is starting like this. So tangent is parallel to the radius at theta equal to 0. At theta equal to 0, right? So this is how actually you will be tracing in case of polar coordinates. Got it? Now for all curves actually it may not be symmetrical about x-axis, right? So suppose if I take r is equal to a sin theta. Can you trace this curve r is equal to a sin theta? Note down this and try to trace r is equal to a sin theta. Okay, so let me trace that. R is equal to a sin theta and then r is equal to a cos theta. So both the things actually I am going to trace it. Now see this. So let us say this is the initial line and then at theta equal to 0, so r is equal to 0. That means this is starting here. Now at theta is equal to pi by 6, that is at 30 degrees, that will be a by 2. So that is somewhere here. And theta equal to 45, so a by root 2. And theta equal to 60, that is a times of root 3 by 2, somewhere here. And then at theta equal to 90 degrees, that is a, so that is here. Now this is as if like, so this is 30 degrees, this is 45 degrees, this is 60 degrees, this is 90 degrees in the opposite direction also. See this, for different angles of theta, I have tried calculating the radius value and then corresponding radius I have identified and I tried joining all the points together. This is how I am getting it. This is nothing but a circle. So r is equal to a cos theta is nothing but a circle. But this is symmetric about the vertical line. Got it? Symmetrical about the vertical line. But if you trace this curve, this will be exactly in the similar manner. This is again a circle, but symmetric about the horizontal line. So this length is nothing but a, and this length is nothing but a. So this is the radius value of this particular circle will be a by 2, but the diameter is a. Even here also the diameter is a, and the equation of the curve is r is equal to a cos theta. So this understanding of the curves in polar form is very much needed when we deal with the areas and volumes in the same calculus topic itself. So when we deal with the integrations and the applications of integrations, so there we are going to trace all these curves. Got it? So this is symmetric about x-axis, this is symmetric about y-axis. Any questions on this? Can you trace a into 1 plus cos theta? R is equal to a into 1 plus cos theta. I didn't get you, Ravindra. What is its half? So you can increase theta value from 180 degrees, but you are not going to get, so you are going to get the same value again, because the radius value is only positive. I think one important aspect actually you people have to understand. So here, when we deal with the xy coordinate system, we can take the values of x positive and negative, y value positive and negative. But in case of polar coordinates, the r value you always have to treat as positive, because radius can't be a negative value, length can't be a negative value. So if you keep on increase the theta value more than 180 degrees, the value you are going to get it as a negative value. So that you have to take it as the positive and then try to identify the radius. Yeah, mirror image. Got it? So mirror image of r is equal to a into 1 minus cos theta. That is, earlier actually the curve is coming out to be like this, but now here it will be like this. This is how actually we are going to get it. Got it? Yeah. Now, can you trace the curve of r square is equal to a square cos 2 theta? A square cos 2 theta. Try tracing this. Anybody got it? So this is as if like the dumbbell shape. So this is the kind of shape you are going to get it. Now here, this is one tangent and this is another tangent. Now if you notice, this value is nothing but when r is equal to 0, then a square cos 2 theta is equal to 0. It implies cos 2 theta equal to 0, or 2 theta equal to pi by 2, or theta is equal to plus or minus pi by 4. So this is also plus or minus, right? Now here, theta is equal to plus or minus pi by 4. This is theta equal to pi by 4 line, and this is theta is equal to minus pi by 4 line. Now at this point, r value is coming out to be 0. That means if you just draw a straight line like this, theta is equal to pi by 4, this is nothing but the tangent at the origin. Got it? So this is also one more tangent at the origin. Now, if you take a theta is equal to 0, then r square is equal to a square. So r is equal to plus or minus a. Now here, see this. So this value on the right side and this value on the left side, you will be taking it. The modulus value of this will be a. The radius length is a, but in the opposite direction. Got it? So this value is a, and this value is also a. So this is how you will be tracing the curve. Now at this particular point, so the tangent to the curve is perpendicular to the radius. At this point also is perpendicular to the curve. At this point, the tangent is exactly parallel. Got it? So this is how you will be tracing the curve. So this is about the curve tracing. Do you have any questions on this? Any questions on this? Okay. Yeah. Great. Yeah. So that's all for today. So thank you. Yeah. Good night.